Our first example of a water flow, again, is going to implicitly assume that our cross-sectional area is 1. And what we're interested in doing is predicting the steady state concentration gradient, which is effectively what C of x is. The word gradient's sort of misplaced here, but it's typically used. And we want to do that along what kind of layer? Let's do 1,000 meters, so 1 kilometer layer. And at one end, we have a concentration of 50 parts per million. And at the other end, we know the concentration is 0. And what's going to happen is there's going to be a diffusion. So at this end, we know it's 50. At this end, we know it's 0. What's the concentration profile going to be in between those two sites? What we're going to do is solve this, leaving v and d as constants for now. And we'll see how that plays out with the help of our Laplace transform. Notice we're not including any external contributions here, so f of x is going to be 0. That'll make our life a little bit easier. Here we see our differential equation with the d moved down here, so basically put in standard form. That's going to make it a little easier to manipulate. Notice that we could solve this with the techniques from earlier in the course, but we'll stick with Laplace transforms because we'll need them in a second. So our goal is to take the Laplace transform of the whole differential equation, and new terminology here, our transform of little c of x, we're going to call big C of s. And what that gives us is the transform of the two derivatives is s squared c of s minus s c of 0 minus c prime of 0. And then we're going to subtract v over d times c prime, which is s c of s minus c of 0. And all of that equals 0. All right, what do we know? We know the initial concentration was 50. We don't know what the derivative is. Instead, what we know, let's put this aside here, what we know is the boundary condition, which is that C of 1,000 meters from the other end. The concentration is simply going to be 0. That means we're going to be solving for this later, so we'll call it A for now and obtain its value before the end. Simplifying here, we're going to have s squared minus v over ds times c of s. And we're also going to have minus 50 s's minus a, and this is also another 50 here. So we'll have minus positive v over d times 50 equals 0. Now we want to find what c of s is, because that's our transform solution. So we'll have our s squared minus v over ds, c of s. Move all these terms to the other side. We'll have 50s plus a minus v over d times 50. And last but not least, we can simply divide through by this term over here. We'll have 50s plus a minus 50 v over d's divided by, let's factor this, we'll have s times s minus v over d. Now this looks a little complicated, but we can take one shortcut and focus on this first term. There the s's cancel, so we end up simply with 50 over s minus v over d. And then we have the second term, which is a little more complex, which will require partial fractions to break into pieces. So this term is fine. This term, when you do partial fractions, when we have something as ungainly as this, though, it's probably easier to work with some constant, and then what we're going to find is that the decomposition is some multiple of that value. It'll be easier if we just work with b instead of this complicated mix of variables here. With that in mind, what we're going to do is decompose b over s times s minus v over d into big A over s and big B over s minus v over d. When we do that, we're going to be able to cross multiply, and we can sub in some values. If we let s equals 0, we're going to get b, little b, is equal to a minus v over d. And that's going to give us big A is the value we started with times d over v in negative. For our next step, we can try v over d, and that'll make this term 0. And that'll give us little b is equal to capital B times v over d. And so capital B is d over v times b. So in fact, we get a nice reciprocal relationship. One's just the negative of the other. What does that mean for our C of S? Well, our first term stays the same. And then we're going to add capital A over S. And capital A was our quantity we started with, A minus 50 V over D's. It'll be negative, and it'll have a D over V multiplier, all divided by S. So that's using this term here with this A value and the little b value. Little hairy, but it's just subbing values in. Last term is the capital B over S minus V over D, and capital B was this combination. So D over V times our initial multiplier on top, all over S minus V over D. And now, though it might not feel like it, we're actually ready to do an inverse transform. Everything we have here on these two terms here are constants. At most, what we might want to do is simplify them a little bit. We might make it a little bit easier if we do that. So we'll rewrite the first term. The second term, the d over v and the v over d cancel, and we end up with negative a d over v plus 50 over s. And in the second term, we can do the same thing, multiplying the d over v, and we get d over va minus 50 over s minus v over d. And at this point, we realize there's one last savings to be had, because 50 over s minus v over d and minus 50 are going to cancel. So our last simplification is that C of s is negative AD over v over s plus 50 over s plus AD over v s minus v over d. And this is fairly straightforward to take an inverse transform. Rewriting our function here, and then completing the inverse transform, we get, this is the transform of a constant, then we get the transform of this constant, so 50, and last but not least, we end up with AD over V times E to the V over D times our independent variable, which is X. So our concentration over the interval 0 to 1000 is going to be defined by this function, with the one missing ingredient being that at 1000 meters out, we know the concentration is 0, so we can use that feature now to solve for A. We get negative AD over V plus 50 plus AD over V e to the V over D times 1000. And now our goal is to solve for A. So we want to group some things. Let's bring this 50 over, and we'll have a common factor of AD over V on this side, and we'll have minus 1 plus e to the V over D times 1000. Now what does that give us? Well, we can divide through by that. So we'll have negative 50. Let's actually take the negative sign for both of these. That'll give us 1 minus 1000 V over D's is equal to AD over V. And then we'll just simply multiply and multiply. And so A is just 50V over 1 minus e to the 1000 V over D's times D here. And so that's based on the speed of the water and the diffusivity, or the diffusion coefficient of the rock that this concentration is flowing through or diffusing through. What does that mean, though, in terms of actual structure? When we plug this back into C of x, our C of x is going to be, we're going to group these two terms, and notice that we have A times D over V, so that's going to cancel out the V's and the D's. So when we plug that in, we're going to have a multiplier that's just a 50 over 1 minus e to the 1000 V over D. We're going to have minus one of those plus an e to the V over dx. And then we're going to have a plus 50. Now that does not look particularly helpful, But if we look at the structure of the graphs of this, it'll turn out to have some nice, simple properties to it. In particular, you'll notice the only x. There's only one x in this whole thing. So essentially, there's some exponential growth or decay going on here in terms of the distribution of concentration, and we'll see how that looks on the next page. If we write our concentration function out, what it boils down to is this formula here. What does this tell us? Well, it tells us at x equals 0, we're guaranteed to have a 50 value because these two terms cancel out. And we knew that because that's how we set up our initial concentration gradient. That was the one of the two known values. The k is selected so that no matter what we choose for v and d, we end up at 0 when we reach x equals 1,000. So let's take a look at the v over d being positive case here. So what we'd have is an exponential growth shifted down by 1, but if we have exponential growth, that's not going to work. So what we must have is k being negative. So what we're going to see is an exponential growth curve inverted that starts at this point and ends at this point. And so what we see, if the velocity is positive here, when the water is moving to the right, what we end up is a concentration gradient like this. Meanwhile, if v over d is negative, then what we have is e to a negative number minus 1. So that'll be an exponential decay. If you work that out, it'll turn out that k is positive in this case. This multiplier will be positive because an exponential decay is just fine. Well, it's also important to note that these diffusion constants are always positive. No one has a negative diffusion coefficient for rocks or sand. So what we're talking about here is the velocity of the water. If the velocity of the water is negative, in other words, it's moving to the left, then we end up with this kind of profile. What's really interesting, and it's not very well covered by this, but we can almost see the transition here, is if we have positive v's, we get an arch like this, negative v's, an arch like this. If we have v equals 0, which is a borderline case, with no water flow at all, we can't really use our solution from before, because when we used a partial fraction decomposition, we assumed that this was not 0. But if we have v equals 0, that's not true. But what it gives us is the border between concave up and concave down, which is just a straight line. And that makes sense if you're talking about diffusion in steady state. If we maintain the concentration at one end at 50 parts per million, the concentration at the other end at 0, then you get about halfway between, you get half of the concentration as it diffuses from one end to the other. So it's a nice way to sneak up on the special case of no water velocity using the two cases where the velocity is positive or negative as extreme cases. The important thing though is that we've generated a prediction. Knowing just the concentration at two endpoints and maintaining those two concentrations, in the steady state, what's the concentration profile in between those points going to be? Well, it's going to be defined by the solution to a differential equation.